Hello and welcome. In this video we are going to look conservation of mass in differential form. For integral form you can go through our earlier video of conservation of mass as well as the meaning of conservation. So here we are just repeating the meaning of conservation statement. So it states variation of a property, in this case mass, inside a considered domain is balance between the amount of property, again mass in this case, entering and leaving domain plus eventual contribution from sources generating that property. So this was a statement which we already have made in meaning of conservation video. You can go through it. So it states in equation wise as d phi dt is flux in minus flux out, which is leaving flux, plus volumetric generation of source, in this case mass, and plus surface source. So let us call this as equation number 1, and this is going to be a main equation for our formulation in differential forms. So in case of mass conservation, we already know that phi is basically property per unit volume. So for phi is equals to rho, which is mass per unit volume in our case. So we also need to formulate something called as flux in this case for a differential form. So mass flux basically defines in our case as mass entering per unit of surface per unit of time. So that is a definition of a flux. So for mass flux we need to formulate this entity. Mass flux is equals to naturally mass, in our case per unit of volume because we are dealing with density now, multiplied by velocity multiplied by area. So this comes out to be flux is equals to rho v bar multiplied by a. So now this area needs to be considered. Okay, so for that we will consider a flow field, any flow field, and let us try to show or mark a small finite differential element which is infinitesimally small. So consider a small differential fluid element. We'll come to this term differential later on. Differential fluid element in the field we called flow field, which is in formulation going to be fixed in space. So Eulerian differential form is what we are going to deduce in this case. Okay, so let us try to sketch or expand this fluid element which we have considered so that we can appropriately show the dimensions and we can work with it. So let us say this is the differential element in exaggerated form. So let us try to use Cartesian coordinate system, right hand system. So this is y, x, and out of that is z. So nomenclature which we have used, as I have said, is right hand coordinate system. Okay, so this is, let us discuss, this is called as y face because perpendicular to that face or surface is y direction. Similarly the other one is y negative. So let us show the top face as positive z because z axis is normal to that. Similarly negative z face because negative z is normal to this. Front surface and back surface, front is positive x face and back is negative. Oops. Okay. Okay, so this is going to be negative x face. Okay, so these are our nomenclatures for identifying faces. The surface to which axis is positive, which is normal, so that is called a positive face. So let us copy this element. We are going to use this for further analysis. So let us try to mark some dimensions on this. Let us try to show this as dx. Okay, and then we have dy, sorry, dz, this should be, because z axis is perpendicular, and this should be dy. Horizontal is dy, vertical is dz. Okay, we are going to use 3 different colors for formulating fluxes in 3 different directions. So this is x. Okay, so let the dimensions be dx, dy, dz, be lengths, what we say, of fluid element. Okay, now let us formulate. So for simplicity of analysis, consider, okay, so let us paste this here. Let us remove scratch of whatever is unwanted. Okay, so let us try to formulate one by one all the fluxes. So let us say now we have new system which is horizontal is x, perpendicular is y, and normal is z. Okay, so these are x directional fluxes now. So left one is coming in and outwards is right face. Okay, so let rho u, which is x directional component, multiplied by ax be mass flux enters the fluid element from left surface, fluid element from left face, and similarly rho, so this is the left face, now right face mass leaves, so rho u ax plus dx, because we have directional increment along that, the mass flux leaves the fluid element. Okay, so from left face mass is entering, right face mass is leaving. So let us copy and try to show other 2 directional fluxes. So we have marked, okay, normal as y-axis, so let us use different color. Okay, so this component is going to show the y directional fluxes. Okay, so for z directional fluxes, so this is the way, from the bottom face it is coming in and outward is top. Similarly back side fluid is coming in and front side leaving. So similarly rho v in this case, now for y directional component of velocity, we need to consider rho v ay will be flux along negative face, negative y face we will say, positive, no, it's negative face y. Similarly rho v ay plus dy flux along positive face. So similarly rho w az will be flux along negative face, and flux along z plus dz will be positive face. Let us mark them as along y direction, and these are along z directions. Okay, so now we need to formulate the area components. Okay, so for areas we'll first find out ax, what we have. So that component, so we already have the lengths dx, dy, dz. So along x we have dy and dz as the area normal. So ax will be equals to dy multiplied by dz. Okay, these two components, yes, dy into dz, and same is for ax plus dx. So area remains constant. Let us, okay, so this is ay, which is dx multiplied by dz now, and is identical to ay plus dy. Similarly, az, which is dx dy, a product of two sides lengths, will be identical to az plus dz. So let us continue with the numbers 5, 6 and 7. Okay, so now to obtain flux, mass flux, at all, let us say, positive faces, because these components are along x plus dx, y plus dy and z plus dz. So these are rho u ax plus dx, rho v ay plus dy, and rho w az plus dz. Okay, so we need to use something called as infinite series, so which were first introduced by Indian mathematician Madhava, Indian mathematician, somewhere in the year 1340 to 1425. So though it is named after Brooke Taylor, English mathematician, and in the year 1715, so we call this series as Taylor's series, and it states that any function at x plus incremental length dx is equals to f of x plus df dx into dx plus second derivative of function with respect to x into dx square by 2 factorial, plus it goes till infinite. Okay, so let us call this as equation A. So similarly, we have in mass conservation, we know that here u, v and w, now they are not ordinary differentials, they are going to be partial because they are functions of x, y, z. So we need to formulate them in partial form. So rho u at x plus dx on the same lines will be going to be rho u plus partial over partial x of rho u into dx plus some higher order terms. So call this as that equation. So similarly, v will be rho v plus d partial over partial y of rho v into dy plus so on. Similarly, rho w, z plus dz, rho w plus partial over partial z of rho w into dz plus. Okay, so higher order terms we usually ignore them because of small ignorable lengths, dx squared, dy squared and so on. So we already have said like the dimension is infinitesimal. Okay, so we need to model these flux in and flux out. So let us consider flux first of all along x direction, and we already have f of x is equals to f of x in minus f out along x direction, x plus dx. So this is rho u multiplied by dy dz and rho u x plus dx into dy dz. So that was the area. So we need to put these terms into these equations. So okay, let us use the blue colored for x directional flux. So rho u So this from equation 8 we can substitute term as rho u plus partial over partial x of rho u to dx multiplied by, so let us complete this entire bracket, multiplied by common area which is ax, and we already know that ax is rho u plus minus partial over partial x and multiplied by ax which is dy dz. So first two terms will cancel off on RHS and we will have directly the flux x is partial over partial x and dx dy dz. Okay, so now similarly we can obtain flux which is along y direction, so identical to x direction. So we have fy minus fy in minus out flux at y plus dy 15. So this flux we already know that rho v minus by Taylor series, so rho v partial over partial y of rho v dy into area ay. So that area was dy into, yes, so that is dx dz. Okay, so that was a flux along y direction. So similarly flux along z direction we can say fz, flux in minus flux out along z direction. So this is rho w minus partial over partial of rho w dz and az. So az is dx dy. Yes, so this is going to be dx dy dz. Yes. Okay, so that is a flux along z direction. Now we need to formulate one more term which is there on the left side, which is d phi dt. Okay, so let us, these volumetric and surface sources we are going to ignore, so we don't have generation of mass. So let us say rate of mass change first of all in mass change. So this is time rate of mass change in a fluid element d phi dt. Now in this case phi is rho, so d partial over partial t of rho dv, and dv we need to model this, so dv infinitesimal volume of fluid element which is going to be product of all lengths. So for a parallel pipe shaped it is going to be dx dy dz. Okay, so we need to now formulate this term. So this becomes partial over partial t of rho into dx dy dz. So that formulates left side of the conservation equation. Now we need to assume no mass sources in a system of surface and volume. So that is, we are dealing with engineering problems, no nuclear reactions. So recollecting all the terms which were in 22, then we have this as kfx which is 14th equation. Let us highlight them, fy and fz. So those are 22, 14, 17 and 20 in equation 1. So this comes out to be d rho dt dx dy dz is equals to negative partial over partial x of rho u times volume minus partial over partial y of rho v times volume minus partial over partial z of rho w multiplied by volume. So we can take this as common from both the sides. So let us say dividing both sides of equation, both sides of equation by volume, which is dx dy dz, and let us rearrange that. So take all the terms to the left. So we have now d rho dt plus partial over partial u of rho u plus partial over partial y of rho v plus partial over partial z of rho w is equals to 0. And this is actually the final form, which we say Eulerian form of conservation of mass in differential form. So can also be written as d rho dt. We can summarize this as del bar dot v bar, rho v bar, is equals to 0. This term was already explained in integration or integral formulation in last video. So here it is directly written. Okay, so these are two different forms of same equation. So these equations 24 and 25 are known as conservation of mass in differential form, also known as continuity equation. So let us try to now deduce some results from them. So as we did for integral form. So let us say case A is steady compressible flow in which density will vary. Okay, so steady here term indicates that partial over partial t of some any property is going to be 0 because it is constant with respect to time. Similarly, so from equations 25 or 24 we can use. So we get this term as del bar dot rho v bar is equals to 0. So this is, or can be written as in differential form as plus partial z rho w is equals to 0. So these are final results. Okay, so let us say B, which is steady incompressible flow. So these terms were already explained in last video. Let us say rho is constant in this case and ddt is also constant 0. So from equation 24 or 25, yes, we can directly write del bar into rho v bar is equals to 0. Rho is constant, so we can take it out since it is a constant. So this reduces to del bar dot v bar is equals to 0. So divide both sides by density of a fluid. We can write this as divergence of velocity is equals to 0, which is del bar dot v bar is 0. So this is a final result again for steady incompressible flow. So it states divergence of velocity vector is 0. Okay, so those equations 25 or 24 can be also be rearranged to get the Lagrangian form because they were deduced in Eulerian form. So d rho dt plus v bar dot del bar operating on rho plus rho into divergence of velocity. So note this term, this is a product rule in calculus of differentiation. So this term can be said as an operator v bar dot del bar operating on rho plus rho into del bar dot v bar is equals to 0. So this term was also explained in last video. So we know that this term is a Lagrangian or material derivative, substantial derivative or total derivative d rho dt plus rho times del bar dot v bar. Kindly note that here d is not ordinary differential, it is total differential. Still velocity is dependent on three terms. So this is a Lagrangian description, what we say. We have alternative form for this, so we can say also divided by rho. We can rearrange this expression as 1 over rho into d rho dt plus v bar dot del bar dot v bar is equals to 0. So that's it. Thank you. These are the results.